we'll make a start. I know it's an unusual day, so I expect people will be dripping in over the next 5 or 10 minutes. But so our speaker today is Professor Jay Hauser, who joins us from UCLA. So Jay is a member of the CMS collaboration at CERN and has been heavily involved in a number of different projects, particularly associated to muons, as I understand it. So Jay's been involved in the CSC and is also leading the technical proposal for the upgrade for the entire muon system. So today he'll be talking about the high luminosity LHC. So please welcome Jay.
Thank you. Well, this whole talk came about because I was talking to one of my colleagues who said that if we don't find anything in the next run of the LHC, he may very well go do something else. And then I thought, well, there's an enormous amount of effort going into upgrading the accelerator and the detector for LHC, both detectors for LHC. And is it really worth it to continue this program and to take more data? So that, I think, deserves a careful look because there's so much activity and effort involved that it's something that we should understand clearly where we're going and why we're going in that direction. So my outline for this talk is I didn't know exactly who's going to show up, so there's a little bit of basic proton-proton collision physics in here, a little bit about what we learned from run 2 using collisions of center of mass energy 7 to 8 eV, and an amount of collisions corresponding to 25 inverse femtobarns of luminosity. Then to say what's going to happen in the next 2 runs, which are called now runs 2 and 3, which will be at 13 trillion electron volts and get us up to more than 10 times as much data as we had at the lower energy. And then at that point, there is a transition to this thing called the high luminosity, or HL-LHC, where it's not raising the energy, but it's simply raising the luminosity by a factor of 10. And the effort that's got to be put in is larger in making that transition than it is in just running the LHC during runs 2 and 3. And of course, there's money involved in that as well. So beyond that, then what might come after the HL-LHC, to put it in a context that's reasonable. So just looking, okay, so when we're talking about going from where we are right now, with run 1 to the HL-LHC, we're really extrapolating out as many as 15 years. And so it's kind of a long enough period of time that it's good to try to put things in a historical context. And so this is, of course, is probably a plot that you've seen before. This is called the Livingstone plot. It plots the center of mass energy of collisions versus the year of first physics for 2 kinds of colliders, electron-positron colliders represented on this dashed line here, and then proton-proton colliders on the solid line here. With the LHC in this plot, this is a bit outdated, having moved off of the solid line plot because of it coming later than would have been expected from that extrapolation. This was an extrapolation that was meant to sort of illustrate a Moore's law of particle physics. Unfortunately, however, Moore's law for computing may be doing well, but for accelerators it doesn't seem to be doing so well. So we have perhaps reached a point where it got harder and harder. The whole idea of all of these machines is that of colliding beams. One started in even earlier years with fixed target experiments where you have a beam that hits a target of matter, but it scales poorly. It scales as the square root of energy of the beam when you talk about center of mass energy. And so in order to restore linearity or a better scaling, that's when we went to colliders about 1970, which is the left edge of this plot, where the energy in the center of mass, energy in the center of mass scales linearly with the energy of the beam. Oh, I should be doing this full screen, I guess.
You were, but for some reason stuff.
Do it manually. Okay, so part of the story is that when you have circular electron colliders, you have a problem with synchrotron radiation energy loss, growing very quickly with the energy of the beam as the fourth power. So because of that energy loss growing so quickly, at some point you're not able to accelerate the beam anymore because your radio frequency cavities are only able to put out a certain amount of energy, and the synchrotron radiation energy loss has grown to a point where it would equal that, so you're not able to accelerate anymore. With proton colliders, synchrotron radiation is not a problem because you're reduced by a factor of the mass of the proton over the mass of the electron, and that's a big, to the fourth power, and that's a big number. So proton colliders have been used from the 1980s onward for some of the important discoveries of particle physics, the W and Z bosons in '83, the top quark in '94, and most recently you've heard about the Higgs particle discovery in 2012. It might have been that these were, this was about a 10-year interval. This might have been about a 10-year interval if the SSC accelerator hadn't been canceled in Texas, and well, here we are. So I don't know if we extrapolate another 10 or 11 years, we're talking about timescales like the HLLHC. So let's see what the prognosis is. Okay, this is just to show that even well, since these big discoveries come infrequently, when they do come, people are pretty happy in our field. This was at CERN when the announcement of the Nobel Prize was made on October of last year. This is the setting for what I'll be talking about today. It's the LHC accelerator, which is underneath the ground along the path that's marked in yellow. The two major experiments that look for the new particles are ATLAS and CMS. My own experiment, and the experiment of the people in this room, I think, is who are from Texas A&M work on the LHC, is also at CMS. And in the bottom, so this is the Geneva area here with the town of Geneva over here, Lake Geneva there, and the French Alps in the background. Okay, so the time scale over here shows you the things that I've been referring to as runs 1, 2, 3, and so on. So run 1 already took place, and the energy was 8 TeV. The next run is called run 2, and is about to start at the beginning of next year. This is referred to as run 3, and then the high luminosity LHC is slated for something like 2024 and onward. The first 3 years of the LHC is all called run 1, and this is the amount of luminosity that was taken in each of those 3 years. The Higgs discovery was made in the middle of the Higgs announcement was made in the middle of 2012, and then we took more data after that time to confirm it. The very first run over here, actually the scale is multiplied by 100, so in fact on the y-axis it's actually a very, very small amount of data that was taken. And the energy was raised from 7 trillion electron volts to 8 in 2012, which gives it a little bit more, helps make the cross-section for high mass physics be just a little bit higher. This is one of my favorite pictures. This is the CMS detector when it's been opened up from its normal running configuration. This is a person down here on the floor to set the scale. It's a system of muon detection consisting of 540 elements called cathode strip chambers, which contain among them about 3 million wires, 300,000 strips, and a nice set of fast and programmable electronics to do the selection of muon particles and their readout. This is a picture of a Higgs decay to 4 muons, or a candidate, I should say, Higgs particle decaying to 4 muons in CMS, which shows in this particular event that 3 out of the 4 are going through that cathode strip chamber system that the Texas A&M group and the UCLA group have been working on. This is just to remind you, I'm sure people have heard Higgs seminars, but these are just some of the measurements that have been made with the Higgs boson using run 1 data. And what's plotted on here is for 5 different Higgs decay modes, what the cross-section that is measured in the experiment divided by the cross-section that the standard model predicts for a Higgs boson particle. And you can see that all of the uncertainties are essentially consistent with the value of 1, but the mean value is that that we're seeing a bit lower cross-section in CMS than expected, but it's within the uncertainty, within 1.5 sigma, so it's just, you would say it's a little bit low. But it's compensated for by the fact that Atlas has a little bit higher than expected cross-section. So they got lucky and we got a little unlucky, but it doesn't matter. Anyway, it's consistent with being an actual Higgs. As far as the mass of the particle that's observed, this is a negative log likelihood plot. You look for the minimum to say which is the most likely point for the mass. And based on the minimal point and the behavior around that, one quotes an uncertainty on a value and an uncertainty on the mass for this particle, which is about 125, 126 GeV. And this is another way of looking at similar data. Forget about the plot on the left. This is a nice one which shows, as a function of the mass of the particle, what the measured coupling is. We've all heard that the Higgs particle couples to mass. Well, what that means is that the coupling constant should be proportional to the mass of the particle that it's coupling to, and that gives you the expectation, which is this dashed line here. And one sees that from low mass particles to high mass particles, one gets a good fit of the data to the expectations there. And it's, so those are all compatibility. Those all indicate that this is compatible with being a Higgs particle. And there are other stories, other analyses of the angular distributions which tell you about the spin of this particle, that it's likely to be a 0+ spin parity particle, which is what we expect. So everything looks consistent with the thing that one learns in graduate school about the Higgs particle. So what's the next step for investigation? Well, there are all these questions about, there's something called fine-tuning, which is that the Higgs mass itself is not very stable with respect to higher order corrections unless you add in new physics. And so that fine-tuning problem points you perhaps in the direction of something called supersymmetry. Another thing that points you in that direction is the idea that at some energy there are these grand unified theories where everything is really one coupling, and the coupling constants merge together at some high energy scale. Without supersymmetry, it's known that there is no such merging of there's no point, or there's no particular energy at which they all merge together. So it doesn't, supersymmetry is a theory that does a lot of things. It unifies, it helps unify the forces at high energy. It stables the Higgs mass. It does also predict that the lightest mass Higgs particle should be under 130 GeV. So we found that. So that's in some sense a piece of evidence for it. And there are also some good dark matter candidates, the lightest supersymmetric particle primarily among them, and that would then help explain where the dark matter might be. Well, so where are we with the status of supersymmetry? People have been looking for it a lot at the LHC and not found it. The question always comes out, have we ruled it out? It's clear we haven't, but there is some tension with the minimal SUSY model, the so-called constrained MSSM. This is Tom Rizzo's depiction of the situation with the various types of supersymmetry, and it may be that we ruled out some some degree of parameter space within the various types of supersymmetry, but there's still room for it to still be alive. It's an important target. That could be at low mass, where it's kind of hidden from us, which means we have to get more data and we have to be more careful about our analysis. Or it could be at higher masses, where we just don't have enough luminosity and still a somewhat close to natural type of theory. So supersymmetry isn't dead, it's just a little having more difficulty than before. This is a compendium of some supersymmetry and exotica topics, just to say that there are a lot of different varieties of supersymmetric theories that have different predictions of what they can produce at the LHC. And this is a little list of the exotica searches that can be done, including extra dimensions, random sundrum models, black holes are in here, and your favorite model can be probably found in that list. This is to be compared with, for the CMS experiment, what the limits are on exotica models. You can see that there's been a lot of people doing a lot of different analyses to try to find something interesting beyond the standard model. So there's a lot going on there. Well, this I think is actually probably one of the best ways to look at what happens when you go to the future, when you try to extrapolate to the future runnings of the LHC and the high luminosity LHC. What's plotted on this in this plot is, let's say that we do an analysis which has a certain reach of maybe 2 TeV, let's say, using the 20 inverse femtobarns data that we've already taken at 8 GeV. Then off of the plot, what's been compiled or what's been calculated is what kind of a mass reach would you have for 2 different situations. With 300 inverse femtobarns and with 3,000 inverse femtobarns. Unfortunately, this was done for 14 TeV, and we're more likely to be running at 13 TeV in the next run. But it should be a pretty illustrative. The difference between 13 and 14 is not that large. And what you can see is, so this is just looking at the parton luminosity ratios and trying to match those up for the different situations. So for instance, if your analysis needed to identify, I don't know, 10 particle decays of a certain type, and that was possible at 2 TeV with present data, that would be possible at 4 TeV with the increased amount of data. And then you can see it would be about 5 or 5.5 with the 3,000 inverse femtobarns. So it's kind of a nice way to kind of think about these improvements in the amount of data. So this factor of 2 that we see in going to 300 inverse femtobarns is kind of like in the old days if you had an electron-positron collider, doubling the energy of that collider. So it's a significant improvement in the physics reach of this thing. Okay, so now when we talk about, so I wanted to first examine the case for what's going to happen when we get this, let's say, intermediate improved data sample before talking specifically about the high luminosity LHC. And so now looking again at this timeline, we're talking then about running from next year for about 3 years, and then after another shutdown, running for another 2 or 3 years in order to collect that data sample. And the luminosities are in small print here, the expected luminosities. This would be about 10 to the 34th, and they would be hoping to get up to about 2 times 10 to the 34th in the following data run. This is an extrapolation for a couple of supersymmetry modes. On the left, it's about supersymmetric top quarks, and on the right, it's about electroweak type SUSY particles. And what's plotted is the current reach, and then in red is while in solid red is the discovery potential with 300 inverse femtobarns, and in red, but dashed, is what you would need in order to do or is the region in which you could exclude this model, any of these models, supersymmetry, with that amount of data if they're not there. And the area in between is sort of like no man's land in terms of it's not clear, whether you wouldn't be able to rule it out, obviously, if it actually does exist, and this might be the area in which you would get 2 or 3 standard deviation excess, and you wouldn't. It's kind of an ambiguous region. So to go to 300 gets us up to the red curves, and to go to 3000 or the HLLHC gets us up to the rightmost curves on these plots. So okay, now you can imagine that there could be a discovery, runs 2 and 3 corresponding to a more or less doubling of the mass reach of these machines. If you did find a signal then, let's say you found 10 events of an interesting type, you would then go, instead of having an event sample of 10 events, you would, with the HLLHC, have 100 events, and you would be able to study something quite a bit more better. So it's obvious that if you do find anything in runs 2 and 3, this high luminosity version of the LHC would be just great. But in addition, it also does extend the discovery reach of this collider. Now, the reason for the HLH, the high luminosity version of the LHC, is that we didn't, or people, everybody didn't design this machine to go above a certain luminosity and a certain running time. It was designed for 10 to the 34th luminosity, which at the time was thought to be enormous and kind of fantastical, I think, when the SSC was designed for 10 to the 33rd, 10 times lower. And with a reasonable running efficiency and the fact that luminosity decreases within a fill and running it for 10 years, you could get up to 500 inverse femtobarns. Now, there's a lot of things that were designed with this in mind and will not survive the additional radiation dose. And that's not only within the LHC, but that's also for the 2 experiments. So certain parts of the ATLAS and CMS detectors, including some very important and expensive elements such as trackers, will need replacement by the time we get there, if we go beyond the original LHC design parameters. This is a pretty busy slide. It's all about the radiation damage to triplet magnets. And I think the most interesting, so I can convince you that there's been a lot of thought about this, but some of the things which are interesting to look at in particular are, for instance, the bonding strength of epoxies can be significantly degraded, the fracture strength of insulating materials decreases, and I think in red here, triplet magnets can experience insulation, mechanically induced insulation failure in the range of 300 inverse femtobarns. So the magnets themselves get enough radiation that they start falling apart, essentially. And so something has to be done. That's just an example. Now that's actually planned for some earlier consolidation, because that can happen before 300. And so there is a plan of consolidation with these new triplets in order to even reach this earlier period where we're at 2 to 3 times 10 to the 34. And then the next phase, so that's called phase 1. Phase 2 is what the accelerator people of the LHC call a real luminosity upgrade. And they're in fact aiming at 10 to the 35th. I'll explain a little bit more about that in a minute, because we're actually not going to run experiments at this luminosity, but I'll explain how those are compatible statements. Besides this luminosity upgrade to the machine, there are going to be these detector upgrades, and so the typical quotation is for 3,000 inverse femtobarns, but we have heard higher numbers like 5,000 inverse femtobarns mentioned from time to I wanted to mention that with high luminosity comes one particular difficulty called pileup, which is that every time that the proton bunches collide with each other, if the luminosity is high, then there's more than one hard interaction going on. And this is an example of an event that has a pileup of 50, meaning that in fact there are 50 places along the beamline where there are interactions going on in this event. And you can see that that's, in terms of being able to reconstruct the physics, that's going to cause problems. Because let's say, for instance, that from this yellow vertex here, there's discovered a very energetic muon particle. Then this will be the interesting collision. The others are probably not interesting. But one has to, for every particle, you have to decide whether it belongs to this interaction or whether it belongs to one of those others. That is a very difficult task to do, and so there's a certain limit to how well we can deal with this pileup problem. And as the luminosity grows to these kind of values, the pileup grows quite enormously. So with 10 to the 34th luminosity and with bunches of protons hitting each other every 25 nanoseconds, we expect pileup on the order of 20. But if that goes to 10 to the, well, if it goes to 5 10 to the 34th, then that 20 becomes 100. And that starts to be very difficult. That's twice as much as this. It starts to be very difficult to deal with. So there's been a lot of estimation of how much pileup can be accommodated or can be dealt with in the experiments. Well, so there are some ideas on how does one either reduce the pileup or reduce the effect of pileup in the high luminosity LHC. So one of these ideas is called luminosity leveling, and that's illustrated in the top right plot. That if you look at what happens with time during a fill, they put these protons in the LHC and then they allow them to collide, and as a function of hours after they're ejected and brought to collision, this is the luminosity profile that you would expect with a normal type of LHC type scheme where you just use the maximum luminosity you can at all times. And this is for a version that would have a peak luminosity of 2 times 10 to the 35th. Now, the initial loss of luminosity is very fast because the luminosity is actually removing particles from the beam quickly. But if you, there are different ways to try to luminosity level. Basically, what you would be trying to do is to lower the luminosity at the beginning by, let's say, you could move the beams away from each other, you could defocus them a little bit. There are various schemes that would accomplish that are being studied. And the idea is that by lowering the initial luminosity, you can maintain it at a level that the experiments can handle, like 5 10 to the 34th, in a quite steady way. And then because you haven't lost as many particles from the beam, you're able to maintain that luminosity for longer and before it starts dropping off. So if you look at the integrals under the curve, yes, you do lose something in terms of the amount of luminosity that you get, but it isn't as severe as you would think it, without thinking more carefully about it. So it looks like it's a good option for this high luminosity project.
So the integrated luminosity is the same?
It's not the same. You still lose.
You still lose.
But I don't have the numbers. It's just the basic concept. And it, of course, depends on where in time you cut and you refill it. So it's all a very practical calculation you have to go through. But it's not as bad as you think. I mean, you really do gain something back. So while I was a little bit under my, what I was scaling, I think it's 140 pileup interactions that you expect at that luminosity. Here's another idea, which is called using crab cavities to take the beams which are hitting each other. Normally, I mean, the beams don't hit each other at completely head-on angles. There's this very slight angle between them. This is exaggerated in this picture. But when they pass through each other, then it's kind of the, it leads to a rather central, well, it affects the shape of what they call the luminous region. And with the crab cavities, when the beams, when the particles are traveling towards the interaction point, they are rotated with these special cavities, so that they're actually passing through each other and with a zero angle, and that affects the profile in the z direction along the beam axis, so that it's more uniform than if you don't do that, where it's quite spiked. The problem with this peaky distribution is that the density of the interactions here at the peak is quite high. So that this is the total pileup, but what's worst is at the center, where you have a very high pileup density, and it makes it just so much harder to separate the particles from the different interactions. All right, so now we turn to what we're hoping to gain from this large amount of data. Well, so the first thing on the agenda is we've just discovered a new particle, the Higgs, and we need to study it. We've done a little bit of study so far, but there's a lot more studying that can be done. And we're talking about 100 times as much, well, 120 times as much data as we have now, and 10 times as much as we would have without this high luminosity upgrade. So it's a big data sample of additional Higgs particles that can be studied quite intensively, and if you see any if you see any significant discrepancies, then that can be a discovery in itself. There's a similar thing with the top and the W mass measurements. There's been, I think at the Tevatron for many years, we were studying the mass of the top and the mass of the W, and trying to measure both of those things as precisely as possible, so we would get an error ellipse, and then you would have various curves that correspond to mass of the Higgs being 100 or 300. I mean, this is basically a cartoon, but it's kind of looked like that. And now that we know that the mass of the Higgs is 126, it corresponds to a very tight line on this plot. If you then go back to the W in the top mass, it may be that if you measure it more precisely, you'll find an error ellipse, which is something like this, and it's quite consistent with that. But you might also find that what you measure is not consistent with that. So that's an interesting measurement to be made as well. And of course, the number of W and top quarks that are produced at the LHC is just, you know, at this point I think it's in the tens of millions, and by this time it'll be in the billions. So you can try to do very specific things to get those measured more better. And of course, you have additional reach in mass and in sensitivity for the other theories like supersymmetry or exotic models. Now, the Higgs boson couplings are one of the topics that's been studied quite a bit. So I showed you a plot like this, showing you the coupling that's been measured thus far with, what's shown here is an arrow with plus or minus 50% on it to kind of guide the eye. What we've done thus far is to measure various modes with accuracies between 10 and 50% on the cross-sections. The couplings of the Higgs, of course, have to be squared in order to get the branching ratios. And so those uncertainties correspond to about 10 to 25% on the measurement of the couplings. And with the upgrade, we'll increase the Higgs data set quite a bit. And so one can reduce those error bars. Now, in order to probe very energetic particles that can come in with new theories of physics, we need coupling precisions which are quite a bit better than what we've measured thus far, and so people have tried to estimate how well will these upgrades do the job. So well, one of the inputs to that calculation is to look at the size of the data samples that you're going to have for Higgs into various modes with what we have thus far in run 1 and what you might get in the LHC. And in some cases, so this one, Higgs to 4 leptons, it looks like it's an improvement of a factor of about 200. Part of that is the size of the data sample, and part of it is it's a slightly higher energy. So that's a pretty simple scaling. In the case of Higgs to tau tau, it looks like instead of 200, the anticipated increase is more like 400. I think, I'm not quite sure to what extent that's including improvements in the detector performance that are anticipated, but you know that these things are taken into account. And then the thing to compare what these experiments can do in terms of measuring the couplings needs to be compared to what theories can predict for the deviations of the couplings. And in some theories, it's clear that one may be able to access to see deviations at the level of 6%. It's probably quite doable. But some of them, like this decoupling MSSM model, it's quite small, and you may not be able to do it with this machine. So this is all detailed in the Higgs snowmass.
These are after taking pile-ups in this time.
Yeah, it's taking everything into account.
So taus are doing better than the
I can't defend this. I don't know what the details were. I think you can go to the snowmass report to figure out what actually has been done. This is a little bit more on this. On the left, you get some projections from Atlas for how well they can do for various decay modes with 300 and 3000 inverse spectral arcs. And there are some rare decays that are interesting. Higgs to mu, for instance, is a coupling to a second generation of leptons or quarks. None of the things that have been, well, it's not on this slide, the previous slide. Thus far, everything that's been looked at is either to a boson or to the third generation. So, you know, if the Higgs was funny in terms of what it was, if it was doing something funny just in the first and second generations, this would be the next thing that you would be looking for. Higgs to Z gamma might be a question about new physics and loops. So here are some interesting numbers. These are for the different couplings to different types of particles, how well CMS has projected that they could do with 300 and 3000 inverse femtobarks. And what the numbers in brackets are the uncertainties in percent. So, and there are two numbers for each box. One is an optimistic projection, and the other is a pessimistic projection. The pessimistic one takes the systematic errors as they're understood right now and just scales the statistics. The optimistic takes the systematic errors and says with more data, the experiment may understand the systematic errors, the causes of the systematic errors better. And by working on that, let's just suppose that they scale down as the square root of statistics. So you get that range, which in some cases can be quite considerable, like between 2 and 5%. So, but you can see that if you want to get down to the 3% level, 300 doesn't quite do the job. 3000 looks like it's what you would probably ask for if that's the criteria that's very important. So anyway, in general, you get about a factor of 3 improvement in the coupling constant measurements. So, okay. This is again coming back to the Suzy discovery. Oh, I think I showed this before, didn't I? Okay. So this I showed before as well, but now I did want to bring your attention to one fact. That if you're looking at this plot and you say, where do we go between 300 and 3000? On the face of it, it doesn't look that good. Like this goes from 6 to 7 TeV. Not that huge of an increase in ability to discover new physics. But the percentage gains with that increased luminosity are actually larger at small mass, where it's not very apparent on the plot. So if we are to go down to, say, this point at, well, let's take the 1 TeV result here for the 300 inverse femtobarns, that actually, you get almost a 2. You almost get a doubling at low mass, which is a bit of a surprise. But it means that you have more, I guess it's rare processes become actually more interesting than the ultra-high mass processes. So, for instance, Z primes are the limits are generally quite high. I think right now we might be 2 point something, but anyway, between these two situations, you don't gain so much. But down here, you gain a good deal more. So the examples that were shown previously are for processes that aren't too energetic. I mean, here we're talking about roughly 1.2 to 1.4, and here we're talking about 0.75 going to about 1100, and those are down in this region here. So it's a little bit deceptive on that, and something to keep in mind. So looking for rare supersymmetric processes is still a really good idea at the LHC. Whereas looking for Z primes, might not be so exciting, in case you want to decide what you want to work on during that time. Okay, now let's talk a little bit about practicalities of all that. This thing, the upgrade for high luminosity is about 10 years off. And so this was a little recap of what we've just been discussing. If the Higgs discovery is the appetizer, then we have a menu in front of us for the other courses. The precision studies, looking for discrepancies, the high mass and rare mode SUSY searches. I should mention that including all of the supersymmetric theories have extra Higgs particles in them, and in fact they're quite fun to, they would be quite fun to discover because the Higgs sector is typically very simple in the supersymmetric theories, whereas everything else is quite complicated with a lot of parameters coming in. And so, so that's something I like personally. And then, of course, all the exotica searches. So thinking about the future runnings, I think that the next few years should be very exciting with the higher energy and the about perhaps 3 times the integrated luminosity just for run 2. And so I think there's very good discovery potential. The following run 3, you might not think to be so exciting, looking at it from right now. It's just a further 3 times increase in data. But it would be very exciting if there was something discovered in run 2, then you would want to, that would be exactly what you would want. You would want to have something like 3 times as much data as a follow-on to confirm anything interesting seen in run 2. So I think it is true that that one branch point would be, if run 2 doesn't show anything, then you might not be excited about run 3. And conversely, if you did find something here, you'd be really excited about that. So we'll just have to see. In any case, it's not really an issue because these are going to happen and they don't require much in terms of additional resources. This is just to add, you probably all know this, but SUSY is something that gives us a lot to do, and we love it because there's all these particles that would be to be discovered. And besides that, there's all the decay modes between, these are energy level diagrams of the various supersymmetric particles in 4 different theories, all of which I think have been ruled out at this point, unfortunately. But anyway, I have the leftover transparencies. But it's basically a dream full employment program for particle physicists if we do discover it. This is a little caveat then about what you can find something, and then well, it doesn't necessarily have to turn out to be real. This is going back to 1984 and the Zeta particle, where they thought they had discovered a new particle, which actually was a Higgs contender at the time. Turned out just to be a fluctuation and not a real thing, even though all the fits look very nice little bumps there. Okay, so now some practicalities of the high luminosity LHC. So it's going to require an extensive upgrade to the machine and the experiments. There needs to be R&D that starts right now, so that has started already. And there need to be substantial construction funds by around 2017 in order to be able to build it on time. Now, we should put some financial perspective into when we say it's an extensive upgrade. Just to set the scale, the CERN annual budget is about $1.2 billion, and US physicists are often used to Fermilab being the flagship laboratory, but at this point, when you look at the actual budgets of the lab, CERN is, 75% of the total of those two labs. I mean, it's the place to be if you want to do something big and expensive. If you want to build a new machine like the ILC to probe the Higgs couplings beyond what the high luminosity LHC can do, that's quoted now as, well, it depends on the source, but Wikipedia will tell you all about it. So I'm just quoting one of the numbers listed. It's around 20 billion. And phase 2, depending on your accounting, is going to be a $1 or $2 billion investment. And so on top of the original LHC investment, it seems like it's maybe a good value, relatively speaking, to continue the program. It's a little bit like renting versus buying a house. I mean, if you can't afford to buy a $20 billion house, maybe you could afford to, let's just scale down by a factor of 1 million, and then we'll, so, okay, it's kind of like that. All right, now, so as for overall perspective, it's clear that if we were to discover anything new between now and the HLHC, we should be doing it, and we should be very excited about it. If not, then it's really the only Higgs factory for quite some time until another machine like ILC or CLEC or another PP collider comes around. And so we need to understand where it is in the context of other machines that are being discussed. So I have a little bit on the other machines. So this is just for Higgs coupling parameters. And what's plotted on the y-axis are the precision of measurement of the parameters. This is the coupling to W bosons, B quarks, photons, and well, use the top quark coupling. And it's comparing the LHC as what we have right now, which this plot is called the LHC 8 TeV, to the 300 inverse femtobarn version, which will be the situation after run 3, the high luminosity LHC, and then there are these machines, the ILC, depending on which version upgraded, they're 500 GeV or 1,000. There's a project called TLAP, there's projects called CLEC, and you can see that the ones that don't exist do a lot better than the ones that exist, but the LHC gets us kind of partway there, and in some cases it actually does pretty well compared to the competition. So also in this sort of pink or whatever you call this color band are expectations for maybe how well you have to do in order to find some interesting discrepancies. But I think that's kind of dependent on the theorist whose model you're considering. Here's a list of some of these machines. There is I've been talking about the high luminosity LHC. This thing is the one which is the most furthest along. There's an idea to build a high energy LHC after the high luminosity LHC, where the energy of the center of mass would be raised. Let's see, go back. That one is actually not on this slide. There's another which is called the VLHC, which would go to even higher energies, which is being considered. This one, the HELHC, is in the same tunnel as being used for the LHC. The VLHC would be using a larger tunnel and a different tunnel. Okay, then there are little maps of where you would put some of these things. If this is the LHC, you could put the VLHC on the kind of in this region where Geneva is here. In the picture we were showing before was over from the mountains looking down this way. This machine would be basically filling the whole of the Geneva area with, not filling, but going around it. And so there are ideas about that. Electron-positron colliders, here's a list of the various versions of the ILC and this thing called CLIC. ILC has been around for a long time and nobody knows where it's going to be built or if it's going to be built. CLIC is a CERN design which is somewhat different and also proposed for an electron-positron collider. These are all linear colliders. That's what the L's mean in all of these. And there are other ideas. So LEP3 would be used, is an idea to use the LHC ring and fill it with an electron-positron collider, kind of going back to where LEP was, but with stronger RF cavities. I think that's unlikely to happen. There's another idea to build a new ring, which initially would be used for electrons and positrons, and eventually for the proton physics, and that would so that's called TLEP. That was the one that did pretty well a few slides back on these projections of the Higgs couplings. And okay, right now, well, the ILC is on here. This is a version of the CLIC. We're kind of running out of time, so that's subject for another discussion. This would be CLIC built in the region of the CERN, and would be running kind of parallel. The Jura Mountains go in this direction, so it would be running parallel to Lake Geneva on the northwest side. And this is this is LEP3. Is just to do it maybe before HLLHC. I think that the machine physicists pretty much rule this out now. The TLEP was the idea of the new 80-kilometer tunnel, then later to be used for PP collisions. So there are all these different things that are kind of in the air, not clear who has the money, because these are all very big ticket projects that would somehow interact with this high luminosity upgrade of the LHC when we talk about the physics that's going to happen. So that's really the end of my talk. I'd like to acknowledge that I picked up slides from a lot of recent meetings. There's a committee called P5, which is evaluating the future of the high energy program in the United States. I've got some from a LHC users organization meeting on the accelerator. And then there was a symposium that had a nice talk about where Kramer had a lot of good slides on these new accelerators or new ideas for accelerators. That's it.
Thank you. I'd say the table you're showing there, showing all the different accelerators, is missing a column with the estimated cost.
Mm-hmm. Yes, absolutely.
Really nice.
And it may be too early to say,
Right.
because it depends on how much people fudge their data.
That's right.
So anything about muon collider people I don't hear.
Opinions vary on the muon collider, from this is very doable to this is impossible to do, so I hesitate to go there. I mean, what would be the luminosity that you would assume for a muon collider? It would depend on how many muons you can get to collide before they decay, and how tightly you could collimate them into a beam. Sounds like it's would be an very uncertain estimate.
So also this clique idea, these are also nobody knows with the technologies.
With CLIC?
So is it like a kind of an established technology?
They have demonstration projects going on. I have to say I'm not an expert on any of these alternate projects, but we we have to start paying attention to understand the context of this LHC machine and its upgrade. We have to understand a little bit of what's going to happen. I think a very important fact that one has to pay a lot of attention to is that at 1.2 billion per year, CERN has actually got the ability to launch large projects. And who else has that ability? I know the Japanese have talked about earthquake reconstruction money going into an ILC. That would be a one-time kind of thing. I don't know. That's kind of like it might or might not happen. I'm guessing no.
Yeah,
So, but what is a fraction of that money that it can actually go into something that's investable? That it can
Yeah, no, I mean,
if you subtract
this-
pensions, funds, and all the
Yeah, I don't know.
building maintenance.
Yes, it's certainly, I mean, you can look at the profile of the CERN budget with year and the peak years of LHC construction. It did go up, and then it's come back down, and now it's coming back up again, I think. If you look at the state of the bathrooms at CERN, they sort of mirror, when they're cutting budgets, they go clean the bathrooms, and then.
So is that an apples to apples comparison, the formula versus CERN? Do they?
Yeah,
technically
these
have
are
the
their
same-
actual budgets, and they have to pay personnel and pension costs.
They pay the same things of those budgets.
Yeah, that's a fair comparison. Although probably the
Switzerland's
salaries
more
at CERN are probably higher than at Fermi-Round.
So what's your money on run 2? What analysis?
Oh,
What we do well?
what should we be working on in Run 2?
Sure.
I don't know. I mean, they kind of have to be looking towards something like this. People who want to look at I mean, Higgs is very interesting too, but the prospect of getting those error bars down to the, where was I? Given that things are consistent so far, how far would you have to go down to increase the error bars enough to convince yourself that something is wrong? It's going to be a slow battle to do Higgs physics to that level. So I think it's still, look at this plot and figure out. I mean, what UCLA has been doing recently was we were looking for electroleakinos. Basically trying to look where, I think that's still a good region to look because that's where you can get large gains from the additional energy and the additional luminosity.
So just question. So electroleakinos through WZ.
Yeah, and not coming from the cascades of squarks and gluinos, just produced in an electroweak manner. So those squarks and gluinos could be at 100 GeV. We don't care, but if the charginos and neutralinos are down at a smaller value, it's okay. You can still
So and
produce
also
them.
Delian production. Like a Z gamma.
Yeah.
So because recently we looked into the electroleakino using PDF, and actually, as you said, this run 2 could be quite important for those things. Like these are kind of rare processes, like you're saying.
No, that's a good idea.
IRC is the one which is going to be built in Japan or China?
I haven't heard about China.
I heard of in Dr. Commons class, China is trying to build the biggest one. I mean linear collider, but I forgot its name.
I heard that the ILC and CLIP were merging collaborations.
In China.
Not necessarily in China, I thought Japan, but I mean,
Oh.
I don't know any details.
They're different technologies.
Yeah,
So-
Yeah,
building-
yeah.
Yeah, China is building some collaboration for this 100 TeV, but it's just at the start.
Is it linear or?
100 TeV.
It's all theoretical.
Yeah.
I mean, I think CERN could propose some large project, but they need to understand what their alternatives are. And they probably would like to wait a little bit before they make decisions as to which way to go, because the difference between an electron-positron collider and a proton-proton collider is one is for high precision and the other is for high mass reach. So it depends on where the physics is kind of pushing you as to which kind of machine you would want to build. But other people want to get in the game, but you could imagine that something like an ILC could be a great Higgs factory, but it's going to be at tremendous expense. So if it's just a matter of shrinking error bars in something where there's no new physics to be gained, I can't see that somebody who puts up $20 billion is going to be happy shrinking error bars on Higgs couplings. I want to see some new physics and some Nobel Prizes.
Any more questions?
Are people talking about, well, I guess it's not really practical in terms of projections. What you can do is, well, what if you don't really run that much for round 2 and round 3? What if you, let's say, you see something in round 2, well, what would you do? Would you go to
There's
HLHC?
Well, there are different questions. Like, if you start to see something around here, do you extend the run for another year? And the answer is probably yes. Why would you wait for 2 more years? I'm sure there will be a lot of gaming, people will be thinking about what is the best thing to do. It will also depend on how much time this really will take. If we get there and if it looks like it's going to take a very long time to do whatever needs to be done, then you might extend this run, or I don't know, there'll be.
Another thing, let's say we're not running at all, what would it take for the LHC to actually get to HLHC configuration? All of the updates, upgrades, how much of the work that's actually happened there was either SPS or...
Oh, you mean during this period?
Yeah. Well, I'm assuming that well, I think that some parts of it already happening towards that.
Right.
They're building something. If you were driving around, sort of, there are new buildings which are apart.
PISOs are already getting upgraded to smooth this process. Yeah. I mean, it's a big, complicated plan. You should get an accelerator physicist to explain it to you if you want to know all about that. I could imagine. Look, there is one of the things that I glossed over a little bit, but for full disclosure. Suppose that you get to the end of this period and you haven't found anything, and you still have all this work ahead of you. Not to mention that this thing will be running for about 6 years. You have time and you have work ahead of you. In a world where you could turn on a dime, you might say, screw it, let's do something else, right? Let's use the money for something else. But the point is, we'll have been spending money on actual construction.
Right. So the question is, how much
you've already
work
spent
is already there,
Yeah.
or that has to happen for the HLHC to actually start?
Most of it. I mean, it's always that way. So it's actually an improved project right now. So it's going to happen. You could imagine that at this point, CERN may be fully committed, but is the U.S. fully committed? Is it possible for the funding agencies in the U.S. to say, oh, you guys didn't discover anything, and we're not so sure, we'd like to do something here in the U.S. and not over there in Europe. Let's turn off the faucet at that point. I don't expect that to happen either, because they have to, by 2017, they have to have concluded their agreement with CERN as to what they're going to do in the future. And they have already started spending some money even for 2014, and they will continue spending money. So they will have already made an investment in the HLOHC by the time that money comes around. But it could, it's like an outside possibility in case budgets were being axed or something. A little bit scary, I would say.
I don't think the DOEs are going to stop funding us if CERN continues to make it run.
Yeah.
But from the LHC standpoint itself, I mean, I'm just looking at the launch shutdown one right now. It's taken 20 months or 15 months to just, I mean, if you're not going into details, you don't know that they are so complicated.
You're saying this could be a lot longer because there's so much.
All they're doing right now is fixing up things which were designed to work at 14 TV and they're still not working like that.
They're fixing something like 10,000 connections.
Yeah, it's a
It's a
lot.
lot.
But the question is, what's what would let's say we're not even running any collisions for physics. What would it take the LHC complex to actually get to the design of the HLHC?
I'm not sure what you mean by what would it take. I mean, in terms of how much time?
Yeah,
But, if we forgot about running, but we
yeah.
just wanted
Forget
to
about
straightforward.
physics running in between 15 and 17 and then the rest.
Yeah, I don't know. I think there's always work going on in the accelerated group, even while we're running on developing things. It probably wouldn't be so much quicker as you. I don't think you can just compress. I don't think you can just take that and compress the time scale in that.
Yeah,
I don't think it
well,
works
it's
that
sort of
way.
with my question. Is it truly, if you just start building it or fixing magnets or putting water balls or whatever else is needed for this to take a lot of time.
Yeah. I mean, there's R&D going on right now. It just needs to get addressed before you can start thinking about it.
Are there still plans to do proton-proton, lead collision?
Yeah.
using the HLA?
Well, actually, that's a good question. I don't know about that.
Is it still lead or is it some other ions? Is it always lead?
Yeah, there were some plans for some other ions. I guess we haven't gotten to that point yet. I mean, Rick runs every year with various choices of what kind of ion.
And by the way, that schedule has been shifting. It changes every time, right? So by the time we reach the high luminosity, let's say, I hope it's still close to 24.
Yeah, I didn't
And
want
it's
to say
not-
too much about that.
Right, and it's not 2030 or something.
Right. The original LHC run was supposed to happen in, well, let's say 2007, and then really happened in 2010 because of various things.
Yeah, but even year to year, there's a few months that it keeps shifting forward.
Well, Long Shutdown 1 has been doing okay. It looks like they're going to be on top.
Yeah, but the original, the starting for run 2 originally was earlier than that, right?
Well, not recently.
Not recently.
I mean,
But if you look at that schedule 2 or 3 years ago, it was at least 4 or 6 months earlier or something.
Okay, I don't remember. Yeah. Schedules do tend to slip. They always slipped a lot more at Fermilab than what I see at CERN.
There are no more questions? Let's thank our speaker again.